Hello everyone. So in this video we are going to talk about RB tree deletion. Already we have discussed what is RB tree, why it is used, and also we have discussed RB tree insertion in our previous discussion. Now in this lecture we are going to talk about RB tree deletion. So let's move. Now RB tree deletion is done as per the binary search deletion. So I believe that you remember that how the deletion is done in the binary search tree. So we have three cases. To delete any of the nodes in the binary search tree, you are deleting a node which is a leaf node, or you are deleting a node which is having one child, or deleting a node which has two child. So if we are deleting a node which is a leaf node, then you can just delete it directly. So let's say you are deleting 78, we can delete 78 from the tree and this is done. In case we are deleting a node that has one child, for example, if you look at the scenario, we want to delete 54, which is having a one child. So we delete this node and this child will connect to its parent. This is how we are doing it. So you can see here that 55 is now connected to 56. In the third case, if we are deleting any node, for example, 56 we want to delete, here 56 we want to delete, and it has two child, left and right. So we have two approaches to proceed. Either we can find the smallest value in the right subtree, or we can find the largest value in the in the left subtree. So here the largest value, we will run the algorithm and we find that this is the largest value. So what we do, we replace this value here, and then we pass on this left subtree to delete this value, because now when you replace 55 with here, so this becomes 55, and then we have two 55s existing now. So what we do is we replace this value 55 here, and then we pass this tree, and then in this tree we delete the 55. So this is to be deleted. So if you look here, this is what we finally get after the deletion. Okay, so I believe that this is already known to you. Now let's look to the deletion algorithm in the RB tree. So basically there are six cases to handle when we do the deletion. So the very first thing is, when we start deletion, we have to start with the binary search deletion. So in the binary search tree, there is basically uh, no issues of coloring. So whatever the nodes we're deleting, there is no issues. But in our RB tree, the nodes are in color. So if you are going to delete any node which is red in color, we are going to just delete it. It's a terminal case. Terminal case means that there is nothing to do and we are done directly. Means it does not violate any arbitrary property. But whenever we are deleting any black node, then there is a issue may arise. When I say issue may arise means it may violate some of the arbitrary properties. So basically, it violates the this black height property. So black height, what is black height? Black height means from the root node to the leaf, all the paths which are possible in the tree must have same number of black nodes. So when we delete any node which is black in color, then it will definitely affect the black height on this path. So this creates an issue. So we need to fix this. So if the node to be deleted is black in color, but it has a red child, then it can be handled easily. We can replace the value of the child with the parent, and also we will going to mark this as a black color. So what does it mean? It means, let's say we have any node. Let's say this is 12, this is 5, this is black color, this is red color, and we are going to delete this node. So what we do, generally, we for this we simply replace this node with 5, and also we change the color this red to black. So the impact of on the black height will have no negative impact, because we delete one black node and then we added one black node. So the black height will remain the same for all the path. Okay, if root node is double black. So now what is double black? Double black is basically a mechanism by which we maintain the RB3 property, and basically we are maintaining the black height property. So what is going to happen? So let's say if this is our tree, let's say this is a tree, something like this, and let us assume that this is black, this is black, this is red, and this is black. Now if you look at this, so here the number of black nodes in this path is 2, and this path is also 2. Now if I am going to remove this node, that means then now this path is going to be shortened by one black height, means it will be having one black node, it will be two black node. So whenever we delete any time black node, then it will create an issue. It will have an impact on the black height. So what we are doing, whenever the black node is to be deleted, we just put a double black. That is an indicator that this path is not being set. It is not fulfilling the black height property, and we need to fix it. So the overall uh, thing that we are doing in the arbitrary deletion is we are handling this double black node. We need to we need to rotate in such a way so that even after deleting this black node, the entire tree still maintains all the properties of arbitrary, which is also maintains the black height rule. So if the root node is double black, simply we can remove it. So let's say in any time you find that the double black is appearing at the root node, then there is no problem. We can simply make it single black, and this is simply solved. As in the case of insertion, when we find that if the root node is red, we can just make it black, and that resolves the problem. Now let us look to the other cases. So case number 3, if DB sibling is red. Now, in the case of insertion, we have seen that all the problem which we are resolving, when I say problem means the issue that comes that violates the property of RB3 are to be resolved by looking to the uncle. Uncle is a parent sibling, and the grandparent. So we look to the uncle and we look to the grandparent in case of insertion. Mean these are the two nodes that help us to fix the problem. In the case of deletion, mainly we are focusing on the sibling of the double black. So in the insertion case, we look to the uncle. Uncle is a parent sibling, and here we will look to the sibling of the node which actually suffers from double black. So if the DV sibling is red, so means the node which is double black is we look to the sibling. If it is red and also it has a black parent, then we are doing these operations. What we are doing, we will be swapping the parent and the sibling color, and rotate the parent in a DV direction. So let us understand a scenario. So let's say we have this kind of scenario. This is your double black, and the sibling is actually red. So we have a big tree, but we are only looking to that portion that matches with the case 3. So this is your DB, and the sibling is red in color. This is red in color. This, let's say, parent is black in color. This is we have deleted, so it becomes double black. Earlier, the node color is black in color. So, so what we do? Swap the color of parent and sibling. So we are going to exchange these color of two, means this becomes red, this becomes black. This is one thing to do. And rotate the parent in the DB direction. And then this parent to be moved in this direction. So this comes down. That means this becomes the left child of this node. This becomes the parent. And then we further see that what that the new tree matches with which kind of case. So we are out of the case number 3, and then we look to the new structure and see that which among the following cases are applicable, and we do accordingly. Okay, so now look to the case number 4. So case number 4 says that if DV sibling is black and both of its childs are black. So this is a scenario when we have this kind of, this is a double black, and this is the node which is black in color. So maybe this is the leaf node, or it may have some more node which are black in color, or even if this is a leaf node, then also it is matching with the case number 4. Okay, so if the sibling is black and both of the children are black, okay, then remove the DV. So in this case, we are actually getting rid of this DB. Actually, we are going to pass this DV, this double black, to other node. It means this DB on this node is to be removed from here. So remove the DB, remove the double black, and add the extra black to its parent. So now this double black uh, to be shifted to other node. Now this double black to be shifted to the parent. Now it all depends on the structure of the RB tree that this double black is going to terminate at this stage or not. Because if this is a red, if this parent is red, this is going to become a black, and we are done with our solution. Means there is nothing to do. We are able to remove this double black. But let's say this parent is already black in color, and when we shift this double black to the parent, then this becomes double black. Means though we have removed this double black from this node, but now we find double black at this node, and we need to still do more processing to remove this double black and make the sibling red, and this we have to change into red color. Okay, so this is case 4. Case 5 and case 6 uh, uh, are like of similar category. So here let us look into case 5. And case 5, when we come out of the case 5, generally we fall into case 6. So what is happening here? The scenario is we have a tree. This is your double black, and then we have a sibling. This is sibling. So DB sibling is black. This is black in color. And then we have a far child from DB is black, but near child is red. So we have it has two child. One child is black. This far child is black in color, but a near child. So means if you when I say near and far, it is in the context of double black. So double black. This is the nearest one. This is the far one. So the nearest one is actually red in color. Okay, so what is required? This is case 5 when your sibling is black, but it has near child is red in color. Okay, and far child is black in color. So what is required? Swap the color of DB sibling and sibling child who's near to DB. So now we have to swap the color of these two. Means this black becomes red and red becomes black. This is one step. Second step is rotate the sibling in opposite direction to DB. So then we are going to rotate from here. So when you rotate from here, so what is going to happen? This node is going to become as a child, and this becomes a parent. And actually, we are into case number 6. Now, what is case number 6? So now have a look here. Case number 6 says we have a scenario that this is a node, this is your double black, and we have a node whose far child is also red in color. This is your case number 6. Now, if you look here, now when you rotate this, so this becomes black, means that this node becomes black here, this becomes black, and this node goes down, it becomes red. So actually, after case 5, you fall into case 6. Now, after case 6, actually, we are getting rid of this double black. So what to do in the case 6? Swap the color of parent and sibling. So whatever the color this parent is having, whatever the color, let's say it is B, then there is nothing to change because this is B, this is B, nothing. If this is red, then we have to swap the color. So we will change the color among themselves between the sibling and the parent, rotate parent in the DB direction, and this parent is going to rotate in this direction. And we remove this. We remove the DB. So this will become the child of this node. This will go up, this will go down, and we also change the color of red to black, and this uh, color of this child becomes black. So these are the 6 possible cases that are applicable during the RB tree deletion. So we'll take one example to understand in a better way and see how these cases are applicable to any real RB tree deletions. Okay, let us look on this tree. This is RB tree. So let us check that is this RB tree or not. So RB tree says that the root must be black. This is black. Every red node must have a black child. Okay, every red node has a black child, has a black parent, and it must have a black height rule property must also satisfy. That means from the root to the leaf, all the possible path must have same number of black nodes. So we can see in this path we have two, in this path we have two, In this path we have 2, in this path we have 2. So black height property is also matched. This is the RB tree. Now we delete uh, node with value 9. So we start from here and then we go here and this node to be deleted. So we are for deletion, this is a case where we have two child. So for the child, we can take either we go to left subtree or right subtree. But one thing to sure that when we do any of the strategy that we use, that strategy is to be used thoroughly for the entire operation. Means we cannot do like when we want delete, we can go with the in order predecessor. But when we are deleting here, we go with the in order successor. No, every time we have to use the same strategy. So we are using the strategy of the in order predecessor. That means finding the largest value in the left subtree. So fine. Here we here we find that this is 9 to be deleted, which has two child. So we will find largest value, which is 7. So we will write 7 here. Means we replace the 7 here and pass the left subtree to be deleted. So when we pass the left subtree for 7 to be deleted, and we find here that 7 is a black color node. Now black color node, when you delete, it will definitely going to affect the black height rule property. So this is going to become a double black, means this node is becoming double black, and now we have to fix this. And this 9 is being replaced by 7. This is still a red in color. Now, we need to look for the cases, that which cases are applicable. So, keep all the cases in like ready with you so that you can just have a look onto the cases and then apply. So, actually, this case is if you look to the how to find the case, which case is applicable, you have to look to the sibling of the double black. So, sibling of the double black is this, and then you have to look to the child. This is black in color, and the far node is red in color. So this is case number 6. Case number 6 is this. So now what what to do? So in the case number 6, what is required? We need to change the color of parent and the sibling. So we'll change this color of these two nodes, and then we have to rotate the parent in the dv direction. This is another step. We will rotate this down, and we remove this double black, and we also change this color from red to black. So let's see what is the impact of doing all this. uh, Let me minimize this figure so that we can get some more white area for drawing. So let me do it this. Okay, so the first decision is delete 9. So already we have discussed this is actually the case 6 is applicable here. So let me write here. Case 6 is applicable, and what is required? Let me also do it quickly. We are going to swap the color here. We are going to rotate from here, and we are going to delete this double black. This becomes 7, and we change the color to black. Okay. So what is the impact? So we will get this tree. We will get 6 here. We get 7 here. Now 7 is here, and that needs to be rotated. So 7 will come down. So 10 will be here, and 7 will be here, and 13 will be here. And we change the color. So 10 becomes red color, 13 becomes black color, and 7 becomes black color, and 6 is also black color, and the remaining 3 will remain the same. So what you see here is that now we can see that the path means from here, from this is again we have two nodes from the root to the leaf. So our black height property is maintained. So we are maintaining the RB tree. So 9 is deleted. Next is delete 3. Okay, to delete 3, let us look to the structure. Okay, let us just look at this. Already we have done with this tree. So let me look at this. So if we delete 3, so what is going to happen? So 3 is again, it's a similar kind of scenario where the node which you delete to be deleted is having two child. We take the left child. We take the maximum value from the left subtree, which is 2 here. So we are going to replace this with 2 here, and then this becomes double black because this to be deleted, which is black in color. Now double black is there. That means we need to fix it. So we again look for the cases. So I believe that you are already having cases in your hand, means you have already noted down all the cases, and you can just uh, view here. So this is basically matching with the case number 5, where your sibling is black in color, but the one child is red in color, which is a near child. So if there is no child, we assume this is a nil node, which is black in color. So this matches with the case 5. So in the case 5, what is required? In the case 5, we will do some operation, and that will turn the case into case 6. So what is going to happen in the case 5? You can have a look on to the cases if you have noted down that we are going to swap the color of DB sibling and the child which is near to DB. So we are going to swap the color of these two nodes. These two nodes color will be swapped. This becomes red. This becomes black. This is one thing. Second thing is we are rotating the sibling in the opposite direction of the DB. So DB is this here. So we will rotate this in this direction. Okay. So what is the impact of this? So let us have a look here. So this becomes 2 here, and this is a double black. And then when you rotate this, so 4 goes up and 5 comes down, and then this 4 becomes black, and then 5 becomes red, and this is your double black. Now if you look at this, still the double black is not removed. We have to remove this double black. Now if you look at this, we already discussed that when we do case 5, and case 5, when you come out of case 5, actually you fall into case 6. Now if you look at this, case 6 is what? This is double black. This is your node, and the far child is red in color. This is the same that we did in the very first scenario. So what to do here? If you remember what we do have to do now, this 2 is black in color. Let me check here what is 2 here. So 2 means this node is red in color. This node is red in color. Okay, and 2 we have deleted. Means this node is we have deleted because this 2 value has already been passed to 3. So this is the scenario here. Now in case, so now we are into the case 6. Now in case 6, what we are doing? Case 6, what we are doing? So swap the color of parent and sibling. So this is the parent, this is sibling. We are going to swap these two colors. This is step number 1 in the case 6. And then we have to rotate the parent in the DV direction. And then we will rotate also this parent to be rotated in the DV direction. Means this is a double black node. And we remove this double black. And we change the color of the red child to black. This color to be changed to black. Okay, so let us make some changes here. So this is our tree. This is 6. This is 10. This is 13. This is 7. Okay, and also note down the color. This is black color, this is red color, this is black color, and then this is black color. And here what we have find out now, after rotation this 2 goes down and 4 comes up. So 4 comes up, 2 goes down, and we remove this, and then we have 5 here, and then this 5 will become black, and then we have to also swap the color of this and this. So actually this 4 becomes red and 2 becomes black. Now if you look at this, you will find that it is maintained. Now if you look at this, so if you go this path, we have 2 black nodes, 2 black nodes, 2 black nodes, 2 black nodes. Now we have successfully deleted uh, node 3, and the tree is still RB tree. Now the next delete is 4. Now again, when we go with 4, so 4 is this node. Okay, so when we delete this 4, it has 2 child. Again we go with the same strategy. We will look to the higher value in the left subtree, which is 2 here. So we replace this value with the 2, and then in the left subtree we delete this node. But when we delete this node, this becomes double black. So we need to mark it double black. Okay, so we delete uh, this node. Fine. So you can see here, when this becomes double black, we have to fix it. We will look to the sibling, and sibling is black in color. And here this said it has no child, so this is actually matching to the case 4. This is case 4. So in case 4, what is required? Case 4, we will remove the double black node. We will remove double black node, but we need to see that double black node is removed completely, or it is going to some pass to some other node. So in this case, for what we are doing, we are passing this double black, means this is not removed, but we are passing this black to the parent. If the parent is red in color, then it becomes black. If it is black in color, it becomes double black. In our case, it is red, so it becomes black. That means actually our double black has been removed. And sibling, we make it red in color. Okay, so let us see the impact of this. So we have come up with this. We are having 6. Then we have 2 here. Then we have here 5, 10, 7, 13. This is black color. This is black color. This is red color. Black color. Black color. Red color. Okay, so now let us check this is uh, arbitrary or not. So if you go in this path, 2 black nodes, 2 black nodes, 2 black nodes. So we are done with node 4. Now node 10. So we'll see here, this is the 10. So again, we will go with the 7 strategy. We replace with the largest value in the left subtree. This is 7. So we are going to replace this with 7. This being a black color, so it becomes double black. And then we look to the sibling. Sibling is black in color. That means this is case 4. Case 4, what we do? We remove this node in double black. We pass this color to the parent. So we pass this color. So this is red. It becomes black. And then we change this black to red. So what is the impact of this? Let us see here. This is 6. This is 2. This is 5. This is 7. This is 13. This is black in color. Black in color. This is red in color. This is black and red. So you can see our red black property is still maintained here. 2 nodes, 2 nodes. Then 10 is done. Now to delete 13. Now 13, if you look at this, this is the leaf node which is red in color. So we can directly delete it. It does not make any impact on the arbitrary, means none of the property are going to violate with this. Then we delete 2. So 2 when you delete, so here it has only one child. So this is the case 1 when you are deleting a black node which has a red child. We simply replace the value here with 5 and keep the color black only and remove this. So we are left with 6, 5, 7. This is black. This is black. This is black. So this is the tree we are left with, and this is the RB tree. So this is all the operations uh, for deletion, and I hope you understood. Thank you so much.